In the study of series, one of the main questions that we ask is, does a series converge or does it diverge? If we're fortunate enough, we'll get to be able to answer the question when it converges. We'll be able to answer the question what it converges to, but that's very rare actually. Along the way, we'll develop several tests which will determine whether or not a series converges or diverges. The first one involves integration. So what I have here is I have the function 10x over x squared plus 1. That's a continuous kind of thing, right? It is a continuous function, in fact, because the denominator is never 0. And then we have a sequence whose terms match the function at the whole numbers. So what I'm going to do is I'm going to go ahead and plot the y values at the whole numbers. And then we're going to make some observations. Because these match, these two, the function and the sequence match, a sub 1 is going to be this at this height. That's 5. A sub 2 is here. A sub 3 is height 3. It's kind of interesting. 5, 4, 3. It doesn't go 2 next, though. A sub 4 is 2 point something-ish, and so on. So you can see the connection between them there. Now I've drawn two sets of rectangles. I've drawn gray ones and I've drawn blue ones. I'm going to outline the first gray rectangle and we're going to think about what's going on there. You want to imagine that the blue rectangles are standing in front of the gray ones. This rectangle is up at height L, a sub 1. It's also of width 1, and so the area will be a sub 1 times 1, so the area of that rectangle is a sub 1. Very similarly, the next rectangle would have area a sub 2. If we continue this, the portion of the graph that's depicted has a sum of the rectangle's areas have a sum of a1, a2, a3 up to a sub 8, which is reflected by the sum over here. Okay? Now, let's look at this rectangle with respect to the curve. The rectangle is a little bit larger than the curve all the way across. Okay? The rectangle is a little bit larger than the curve. So that means the sum that we just talked about is going to be greater than the integral along this entire region. Well, the integral started at 1 and it would end at 9. So the integral from 1 to 9 is going to be less than or equal to the sum from 1 to 8. Let's look at the blue rectangles. This first blue rectangle, its height is, it's what happens at the right end point at 2. So at 2, that's a sub 2. That's height a sub 2 with 1. And so this is a sub 2. And then we'd have a3, a4, a5, a6, a7, a8, and a sub 9. How does the area of the blue rectangles compare to the area under the curve? Well, this time the curve is above the rectangles we've just outlined. And so the integral from, once again, 1 to 9 will be greater than or equal to the sum from the sum of a2, a3 up to a sub 9. So notice the little shift in the limits there. So there's this beautiful connection between integrals and series when certain conditions arise. First of all, the function has to be decreasing, okay? So the function has to be decreasing, and if it's decreasing below the x-axis, that's a little bit weird, so it has to be positive. And then weird things can happen when the function is discontinuous. So we want to make sure the function is continuous as well. But when the function is continuous, positive, and decreasing, there is a connection between the convergence of the series and the integrals. And that's what's the integral test. The integral test says if we have a continuous positive decreasing function on the interval from 1 to infinity, and a sub n, the sequence terms match the function values at the positive integers. If those are all true, then the series is convergent if and only if the integral is convergent. And this, okay, we've talked about this in previous videos. The if and only if part is a two-way street. If the series converges, the integral converges. If the integral converges, the series converges. If you negate both of those statements, it's also a two-way street. If the series diverges, then the integral diverges. If the integral diverges, then the series diverges. So if I want to know if a series converges, I can look to see if its corresponding integral converges. Now, a little language break. This is not stated quite as such, but it's what we call a conditional statement. If f is continuous, positive, and decreasing, then the series is convergent if and only if the integral is convergent. Okay? The part before the then, the f is continuous, positive, and decreasing, those are what are called the hypotheses. These are the conditions. As you do these problems, you must write something about that. So you must tell me that this function is continuous. You must tell me that the function is positive, and you must tell me it's decreasing every single time. Okay? Now I'm going to tell you a little bit of a way we can relax this a bit. It may not have to be all of these things from 1 to infinity. Sometimes this is the most common thing that gets messed up. Sometimes the function is increasing, maybe let's say till 4.5, and then it's decreasing from that point forward. Well, if it's decreasing from some number all the way out to infinity, maybe not 1, but maybe 2, 3, or 4 or something out to infinity, we can still use the result. You just have to be careful what happens before that smallest number. Make sure weird things aren't happening. Okay, we're going to use the integral test to confirm that the harmonic series diverges. Now, the harmonic series, you'll remember, is the series of 1 over n. 1 over 1 plus 1 over 2, and so on. The harmonic series pops up over and over and over again, and it's a really nice example of a series where the terms, 1 over n that is, go to 0. When n is really large, 1 over 0 is very, very small, close to 0. The terms go to 0, but the series diverges. Okay? In order for a series to converge, yes, the terms do have to go to 0, but they have to go to 0 fast enough. Okay? 1 over n, the terms aren't going fast enough. If someone tells me a series converges, then I know for certain that the terms go to 0. But once again, those terms have to go to 0 fast enough in order for the series to converge. What I'm going to do is I'm going to create a function. I'm going to let f of x be 1 over x. Where does that 1 over x come from? It just comes from changing all of the n's in my sequence to x's. Now, let's talk about 1 over x. X is going to be greater than or equal to 1. So f is positive because x is greater than or equal to 1. 1 divided by a positive number will be positive. F is continuous. Ooh, wait, no it isn't. F isn't continuous if x is 0, but that's not really in our range of values. So that's okay. And f is decreasing on the interval from 1 to infinity. Now, I didn't convince myself as to why that is, but if the denominator gets larger, the whole fraction gets smaller. Okay? Now, that's kind of a non-calculus way of looking at it, but it's pretty convincing. You can look at it in a calculus sort of way by taking the derivative and showing it's negative. Our series will converge if and only if the integral converges. So let's look at the integral. I want the integral from 1 to infinity of 1 over x dx. Well, this is an improper integral, so we have to write it as the limit as b goes to infinity from 1 to b, 1 over x dx. The antiderivative is the natural log of x, which we evaluate from 1 to b. We substitute those values in, and we end up with the natural log of b minus the natural log of 1. I love the natural log of 1 because it's 0. All we need to know is what's happening to the natural log of b. Oh, well, the natural log of b, natural log graph looks something like this. Yes, this guy keeps growing. It grows very, very slowly, but it does grow. Okay, so this approaches infinity. The natural log does keep growing forever. Since the limit is infinite, the integral diverges, so the series 1 over n going from 1 to infinity, diverges, you also want to state the test by the integral test. You don't have to capitalize it, but I did. Okay, so that's how the integral test works. Let's look at another example. I have the series n over n squared plus 1 squared. Does it converge or diverge? So what we're going to do is we're going to make a function out of this. This is x over the quantity x squared plus 1 squared. And since I start at 1, let's start at 1. We're going to look at the integral from 1 to infinity of x over x squared plus 1 squared dx. Again, it's an improper integral, so we have to treat it as such. We look at the limit as b goes to infinity, integral from 1 to b of, I'm going to do a little bit of maneuvering here, x times x squared plus 1 to the negative 2 dx. The reason I knew to do that, or was tempted to do that, was because I'm looking ahead. I'm saying, hey, the stuff inside the parentheses there has a derivative of 2x, which matches the x in the numerator up to the constant of 2, constant factor of 2. So I'm thinking I'm going to make a substitution. In the denominator, I would end up with u squared. When I integral 1 over u squared, or anything over u squared, we bring the u squared to the numerator and make it u to the negative 2. So that's why I did that. So over off on the side, I'm going to let u be equal to x squared plus 1, which means that du is 2x dx, which means we get 1/2 du equals x dx. Okay. When I do substitution, I like to change the limits of integration. I'm not such a big fan of doing that with improper integrals, so I'm not going to do that. So I'm going to put the 1/2 from the substitution. I will go from 1 to b, and then we end up with u to the negative 2 du. So just to highlight where things came from, x squared plus 1 is u, so that's u to the negative 2. X dx was 1/2 du, and there's the 1/2 and the du. Find the antiderivative. We get the limit as b goes to infinity of 1/2 u to the negative 1 from, we've got to be careful, this is from x equals 1 to x equals b. We've got to resubstitute. I'm going to go ahead and bring the 1/2 out front. And I'm going to go ahead and substitute things in. So u is x squared plus 1. It's u to the negative 1. So we're going to do 1 over x squared plus 1 from 1 to b. And I notice right now, you're probably all saying, hey, you forgot the negative. Yes, there should be a negative here. When I add 1 to the negative 2, we get negative 1, and then we have to divide by the new exponent, which is the same as multiplying by negative 1. So I've got a negative here. I was thinking ahead and realized I was missing something. So we've got the limit as b goes to infinity of 1 over b squared plus 1 minus 1 over 1 squared plus 1. And here we go. I've got the negative 1/2. As b goes to infinity, 1 over b squared plus 1 will go to 0, minus 1/2. Well, that's 0 minus 1/2, so that limit is just negative 1/2. We get positive 1/4. Okay, now we haven't done our function analysis yet, but I just discovered that the integral converges. The integral converges to 1/4. How about the function? What do we need to say about that? Well, we need to confirm it's continuous. So is that continuous? Well, because it's a fraction, the only thing that I would really need to worry about is if the denominator is 0. It's not. So I should say f is continuous. Is it positive? X over x squared plus 1. The numerator is always going to be greater than or equal to 1. The denominator is squared. It's going to be greater than or equal to 0. It'll never equal 0. So it's positive. F is continuous. It's positive. And there's one other thing we have to check. We have to make sure it's decreasing. And you can look at a graph of this function. You can take the derivative and show that the derivative is negative all the way. But regardless, it is a decreasing function. So the series converges by the integral test. Okay, that's the series that converges. Yes, the integral converge. The integral, here's a question that I often get. The integral converges to 1/4. So does that mean that's what the series is equal to? Unfortunately, no, that's not what that means. We don't know what the integral converges to. We're going to talk about the remainder theorem in just a little bit here and look at an example of that. But this is not the value of the series. For our next example, we have another series of a rational function. Let's see what we have here. I've got n squared plus 2n plus 3 in the denominator. I have n plus 1 in the numerator. So I'm going to make a function out of this. X plus 1 over x squared plus 2x plus 3. Okay, so let's go ahead and do the function stuff first. F is, well, I'm going to go for the low-hanging fruit. Everything is positive. X is a positive number, and we're adding things all over the place. So F is positive. The only time F could be discontinuous is if the denominator is 0. If I graph y equals the denominator, x squared plus 2x plus 3, it looks something like this. This is at -1. Okay? And I see from this that that's always positive. Okay? It's never 0. That's the important part. It's never 0. And so, well, I guess we could have done that analysis before. It couldn't be 0 because everybody else inside is positive. So F is positive or continuous. And once again, if you look at a graph of this function, it's going to be decreasing. Also, you could use the derivative. That's a lot of work, but I'm kind of convinced that it's decreasing because the denominator is x squared, the numerator is x. Those are the highest powers. As x is really large, those other guys really do not have much of an influence on things, the 1, the 2x, and the 3. And so this behaves a lot like 1 over x. Since f is continuous, positive, and decreasing, we can use the integral test. So we'll look at the integral from 1 to infinity of x plus 1 over x squared plus 2x plus 3. Again, we need to write that as the limit as b goes to infinity, integral from 1 to b of x plus 1 over x squared plus 2x plus 3 dx. Okay, this is another one where I see substitution is going to be really helpful. The derivative of the denominator is 2x plus 2, which is a multiple of the x plus 1 in the numerator. So u equals x squared plus 2x plus 3. du is 2x plus 2 dx. Put parentheses around that. If we factor out a 2, we get du is 2 times x plus 1 dx. So here we have another 1/2 du business. 1/2 du is x plus 1 dx. So let's see what we end up with. The limit as b goes to infinity, I'll bring the 1/2 from my last little bit there, the x plus 1 dx is 1/2 du. Integral from 1 to b. And then x plus 1 dx became the du. So we get du, and that denominator is just u. Now this time I did not bring the stuff up as u to the -1. I could, but I usually forget then what the antiderivative of that is. So I recognize this one, the function whose derivative is 1/u is the natural log. So this is the natural log of u. I'm going to evaluate it from 1 to b. But remember, that's x equals 1 to x equals b. We need to resubstitute. We've got the limit as b goes to infinity of 1/2 natural log of u was x squared plus 2x plus 3. We want to evaluate that from 1 to b. I'll pull the 1/2 out front. Limit as b goes to infinity of the natural log of b squared plus 2b plus 3 minus the natural log of 1 squared plus 2 times 1 plus 3. The only place where I see a b is in this first little bit, okay? And remember that b is going to infinity. Well, as b goes to infinity, this b squared plus 2b plus 3, this also goes to infinity. As we take the natural log of a larger and larger number, as we did with the harmonic series example, the whole thing is going to go off to infinity. And so our series, the series diverges. Since this improper integral diverged, the series diverges by the integral test. Okay, so the integral test, I will confess, is not a very exciting one. We don't see it very often, but it does come up from time to time. You won't see it a whole lot in some of the things you do later on, but it is important. Okay, we have something that's called the remainder estimate for the integral test. Okay, so suppose we have a function f of k is equal to a sub k. So the terms of my sequence match the function at the whole numbers, where all the conditions of the integral test are met. The function is continuous, positive, and decreasing when x is at least some number m. And the series converges to some number s. Now, we don't know what s is. Most of the time, we don't know what s is. We're going to introduce a little new creature called the remainder. R sub n is whatever the true value of the series is minus the nth partial sum. Now, it's not listed in here anywhere, but what is the s sub n? S sub n is the nth partial sum, which you will recall is the sum of the first n terms. So what is this all about again? Okay, R sub n is the true value of your sum minus the nth partial sum. The nth partial sum is an estimation of the true value. So this is basically an error. Okay, that's why we call it the remainder estimate. This is the error. How far off are we? Well, it turns out that the how far off we are is going to be trapped between the integral from n plus 1 to infinity and the integral from n to infinity of our function. Okay? So this will give us how far off we are from the actual value. Okay? So we'll do an example of this to illustrate. I have the series n equals 1 to infinity of n to the fourth plus 1 underneath for n, and we want to find s sub 6. We need to know the error. Okay, so let's first find s sub 6. I've calculated it here for us. S sub 6, we stop at the sixth term of your series, and it's about 2.7296 blah blah 390. Okay, so all that business. So that's not too hard to do. Now we want to find the error. Now I'm going on the assumption here that my series converges because of the directions that kind of implied that the series converges. And in fact, we'll look at how we can show this series converges later using a different test. You can do the integral test, and we're going to kind of do it in part here. You'll see all the tools you'll need, but later we'll do it using a different test. All right. We were asked to find the error. The error is r sub n, r sub 6 in our case. R sub 6 is the true value of the integral, which we don't know, or the true value of the series, which we don't know, minus s sub 6. Okay? Well, I'm not going to say that's what the error is. I'm going to use this integration technique to get an estimate for what the error is. I'm not going to compute this because I'm not going to know what s is equal to. So what we'll do is we will, in our case, n is equal to 6. We're going to look at the integral from 6 plus 1 to infinity of our function. So I'm going to change my function to 4x over x to the 4th plus 1 dx. Okay, and then I'm going to look at the integral from 6 to infinity of the same business, 4x over x to the 4th plus 1 dx. The error will be trapped between those two values. So we'll get a good idea of sort of the minimum error and the maximum error we have. We really don't need to do both of these. I think once we do one, we can do the other pretty quickly. So I'm going to erase this second one. Okay, and the first one, this is a tricky one to do. I'm going to sort of lead us down the right path. We need the limit as b goes to infinity. The integral starts at 7 to b, and I'm going to give us a little hint here. I'm going to have 4x dx divided by, now the reason I'm doing this is because if I think about substitution, if this were a nice, easy substitution problem, the derivative of the denominator would be equal to the numerator. The derivative of the denominator is x to the 4th plus 1. The numerator is 4x, but not 4x cubed. For x, well, x, let's just think about x. X comes from the derivative of x squared. So can I reproduce x squared from the denominator? I certainly can. It is x squared, quantity squared, and then plus 1. So this is a really sneaky kind of integral. Okay. So over here off on the side, I'm going to let u be equal to x squared. Du is 2x dx. Now I don't have 2x dx, I have 4x dx, right? Okay, so I need to multiply my du by something in order to get 4x. Well, to get 4x, I would need to multiply 2x by 2. So I'm going to need to multiply that left side by 2. So 2 du is 4x dx. So we have the integral from as b, oops, not the integral, the limit as b goes to infinity from 7 to b of 4x dx is 2 du, and the denominator is u squared plus 1. Now, I didn't really say why I was doing that, but now maybe you can see why I was doing it. I end up with u squared plus 1 in the denominator. That's an arctangent function, okay? So we're going to end up with the limit as b goes to infinity. This is going to be 2 times the inverse tangent of u from 7 to b. Limit as b goes to infinity. We have to resubstitute before we can do anything else. 2 inverse tangent of u is x squared from 1 to b. This is the limit as b goes to infinity of 2 times the inverse tangent of b squared minus 2 times the inverse tangent of 7 squared. Okay, now this is some pretty obscure knowledge that we're going to get here. Inverse tangent of b squared. Let's just think about b squared. b is going off to infinity. So b squared is also going to go to infinity. So I'm taking the inverse tangent of a larger and larger numbers. I'm going to draw the inverse tangent function for us. If you graph it on the calculator, you'll see it looks something like this. But it's really hard to determine what it's leveling off at. It does level off. It levels off. Okay, where does it level off? Well, it levels off if you trace it out there. It's like 1.5 and some change, 1.5 and some change. If you double that, you get 3 and some change. What number do we know that's a little bit bigger than 3? 3.14. The arctangent approaches pi over 2. Okay, so this is a really strange one, but we're going to end up with 2 times pi over 2, so those 2's will cancel, minus 2 times the inverse tangent of 49. If you simplify, this is pi minus the 2 times the inverse tangent of 49. Okay, we'll get a decimal approximation for that. Now, you can probably think through what would happen if you do the integral from 6 to infinity of this business for x over x to the 4th plus 1 dx. The only thing that's going to change is where that 7 ended up in our first one. The 7 was here, that was the lower limit. Our lower limit is 6. Where'd the 7 go? The 7 went when I substituted in, 7 squared was the 49. So the 49, instead of being 7 squared, is going to be 6 squared. So you don't have to do that whole business over again unless you really liked that, and I didn't. So the inverse tangent of 36. All right, so I'm going to erase a little bit here. That means that my remainder is trapped between these two values. Okay, so pi minus 2 times the inverse tangent of 49, the remainder for the sixth partial sum, it's going to be between these two values. When we calculate these, we see that our remainder is somewhere between 0.040811 and 0.055541. Okay, so wait, what does that mean? Okay, the true value is off of the estimated value here that we got from the partial sums. The true value is off of that value by somewhere between 0.040811 and 0.05541. Okay, so I'm going to erase some stuff so we can do a little bit more work up here. First, let's represent what R6 is. R6 is the difference between the true value that we do not know and the partial sum that we calculated. Well, let's replace S6 with what we had the approximation for. So now we have S, our true value, minus the approximation. I rounded it so we have the matching number of decimal places. And now if I add this value, if I add that across the inequalities, we'll get an estimate for where we'll find the true value of this integral. And we see that the true value of the integral is between 2.770451 and 2.785181. So the integral test does give us a way to estimate the sum, but it doesn't necessarily give us a way to find what the sum is equal to. All right, for our last example here, we're going to look at something that's known as the p-series test. The p-series test is a way to look at a series and just get a quick, hey, it does converge, or quick, hey, it does not converge. 1 over n to the p is called a p-series. We want to know for which values will it converge. I'm going to treat them in two separate cases, and we're going to go through it a little bit quickly so we can get to example 5 here. When p is equal to 1, we have the harmonic series. So that diverges. We know that so many ways. When p is less than 1, we end up with the integral from 1 to infinity of 1 over x to the p dx, which we do the improper integral business, and I'm going to go ahead and take the antiderivative right away. Well, this is x to the negative p. When we add 1 to negative p, we get negative p plus 1. We have to divide by the new exponent. So the excitement is taking place here. If p is less than 1, let's think about this. If p is less than 1, we're taking essentially 1 minus p. You have a number that's smaller than 1. Negative p plus 1 will be positive still. Okay? It'll still be positive. So that b to the negative p plus 1 is going to be b to a positive number. B to a positive number is going to race off to infinity. So this is infinite, which means it diverges in this case. For case 3, when p is greater than 1, we end up with essentially the same integral. So I just kind of rewrote everything. But let's think about that now. What is negative p plus 1 going to look like now? Negative p plus 1 will be negative. You have a number that's larger than 1, which you're subtracting from 1, you'll get a negative number. Okay? So what that means is here you have b to a negative power, and b is getting really, 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 really large. Okay, well, a negative exponent says throw me into the denominator, make me positive. So like b to the negative 0.1 would be 1 over b to the 0.1. 1 over b to the 0.1 would be 1 over a very, very large number, so that's going to go to 0. So this guy goes to 0 this time, which means that this guy overall will be equal to, I'm going to do a little bit of work with the negative in that denominator, it's just going to be 1 over p minus 1. So it converges here. So case 3 is when it converges. So the p series says the series 1 over n to the p converges if p is greater than 1, and it diverges if p is less than or equal to 1. Okay, I made a comment once before that the series, let's look at 1 over n, we know that diverges, right? We know that diverges. This is a series where the terms go to 0, but the series still diverges. I made a comment that the terms have to go to 0 fast enough in order for it to converge. I know the harmonic series well. I know it diverges. If I eke the exponent there, right now the exponent of n is 1. If I eke it just by a little bit, 1.0002, it's going to converge. And that's because 1 over n to the 1.002 is going to 0 fast enough, a little bit faster than 1 over n goes to 0. It's going to 0 fast enough for the series to converge. So just really quickly, let's do a couple examples here, determine if each of these converges or diverges. 1 over n to the 0.9. Well, in this case, p is equal to 0.9, which is less than 1. So this guy diverges by the p-series test. Interesting. Okay, this next sum, the 10 doesn't need to stay on the inside. If it converges, I can pull it out. So 1 over n to the 4th. Well, in this case, we have p equals 4, which is greater than 1. So it converges also by the p-series test. Okay, and in the first example, I really should have said that 0.9 is less than or equal to 1, so it diverges by the p-series test.